This lecture on probability distribution, what we've done before, that what is sample from random experiment, what is sample space, outcome, and the event space. And we know the any subset of sample space may not be event. We can suitably choose some event, and then the collection of all event is called event space, and that must be sigma algebra. And then we discuss on what is called probability measure. It's sort of measure with some total probability 1, total measure 1. And then we introduce the concept of random variable. And what is random variable? Random variable is nothing but from a probability space. This is sample space and the event space, and together with the probability is called probability space. This random variable actually a function from sample space omega to r, but the actual is function from omega to r, but is we can visualize this as a function from the triplet to another triplet, and this is called q, and q is actually the probability distribution of x induced by p. Then how do you define this r is a real set, and this Borel sigma algebra on r, and that x must be measurable by function. Random variable must be measurable. What is the meaning of measurable? Measurability means there is a the x inverse is defined from this is not the inverse of x. This is the inverse image. So that defines on basically on the sigma algebra over r, that is Borel sigma algebra to script x, sigma algebra p. So x is a function from omega to r, but this x inverse is not the inverse of x. Remember that x inverse is actually set inverse, and that is defined on the sigma algebra of over r. That's Borel sigma algebra to sigma algebra over omega. How do you define that? That we define x inverse b like that. We define this like set of all omega belongs to omega, such that x omega belongs to b. And if x inverse b not belongs to script s, then this x is not a random variable. So x is a random variable if this condition hold, that x inverse is a function. Once x is a random variable, x inverse is a function from the inverse. It is not the inverse of x, that's the inverse image of x is from Borel sigma algebra over r to s, script s. Now we have to define that q. That q is q of b. We have to define the q is a function from, now remember that q is a probability on r, so it must be a function from Borel sigma algebra to 0 1. That q is a probability. Now q of b for any Borel set of r, remember that s is a real valued random variable, unless otherwise stated is real valued random variable, but x can be complex valued, or x can be that vector valued any other thing. That in that case we mention that x is complex valued, right? Unless if anything is mentioned, then we assume that x is real valued random variable. So xb qb is nothing but that p of x inverse, that b. This is the idea. That is actually we call it a p suffix x. That is a p compose x inverse, that function. So what is this? So this is script is here, and then we have this Borel sigma over r, and there is a function from Borel sigma to script s, and there is a function, probability function from this. Okay, better I at this site. From to this to script s, and this there is a function from this probability function 0 1, and we define this function such that the diagram commit. What do you mean by diagram commits? That means if you go this side, this arrow, or this direct arrow, these two are same. That is q. So q equal to actually p compose x inverse. So this is called probability distribution of x induced by P, induced by P. So why this is first of all, why this is probability? Why this should be a probability measure? So to prove that, our theorem is that Q is a probability distribution. Q is a probability measure. So we have to prove that the Q is also a probability measure. So how do you prove that? The proof is this: that QB is positive, greater than or equal to 0. That is obvious because this is ultimately, this QB is the probability of something, some set. And next we have to show the Q of R equal to 1. The whole set that should be 1. And what is this? This is Q probability of that X inverse R. That means the set of all such omega belongs to omega such that X omega in R. But always X omega is always in R. So for every omega, this X omega, that means it is omega. But we know that probability omega is 1, so we have this. So total probability is 1. Next, we have to show for disjoint set the sum. So take B1, B2, Bi belongs to that Borel sigma algebra over R for all I 1, 2 up to dot 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 dot. It is a countable set. Then what we have to show, that we have to show that this Q of union of the one more thing, that this should be disjoint for all I not equal to J. Now we have to show that for the sum of union of this set, the probability is the sum of this each probability. Now what is this? This is probability of X inverse this, and we see in the previous lecture that this is the interesting property of a set inverse, that is actually union of the X inverse Bi. So X inverse A union B is just X inverse A union X inverse B. Not only for the two sets, it is for finite as well as for the countable union also. So this is true for countable union also. So this is true for countable union also. So this is just property of this inverse set inverse. This is simple mathematical property. It is nothing deal with probability. Now this, we know this is sum of this X inverse, probability of X inverse Bi. But to write that, we have to show that the X inverse Bi must be disjoint. Otherwise, we can't write it. So we have to show that X inverse Bi intersection X inverse Bj is phi. But this is X inverse Bi intersection X inverse Bj is just X inverse Bi intersection Bj, and this is X inverse phi. So this is X inverse phi. This is X inverse phi for all I not equal to j, and X inverse phi is just phi. So that means it's a disjoint set, and since it is disjoint, we can write that sum of all probabilities, and this is actually Q of Bi. By definition, it is Q of Bi. So that means that Q is a probability on R. So what we actually show that this is actually that R Borel sigma algebra over R, and that Q function, that Q, this is a probability space. Is a probability space. Now remember that Q is a set function. Remember, Q is not a just function from real to 0, 1. It is a set function because the input of this Q function is a set, because it's a probability. But the set function is very tough to handle. Why? Because there are several sets. There are huge number of sets in Borel sigma algebra. So there are huge number of sets. Some sets are actually out of our reach. So discuss on that set is not easy. So we have to then find a proper function on R. We have to create a function on R such that that function is equivalent to Q. What is the meaning of equivalent? That means we define the Q, that function from Q, and but that function is on R, not on the Borel sigma algebra, and that Q can be again reconstruct from that function, and that function is a real valued function. We define that function, which is called distribution function. We define a function which is called distribution function. Distribution function. So now it's a very important concept, distribution function. This distribution function is from R201. So this is again a probability, but this is a distribution function. It is not a set function. It is not just as a probability of any set. It is some special type of set. So what is this function defined? So for any all x belongs to real number, we define fx like that. Fx is just nothing but the q of that minus infinity to x, this set, probability of this set. And what is this? This is nothing but probability of x inverse this set. And by notationally, what we write that? We write this as, sometimes we write x less than or equal to x. This is the same thing. That set is. And properly mathematical notation, we should write omega belongs to omega such that x omega less than or equal to x. That is the proper notation of mathematical notation. That probability is called fx. So fx is set of all probability of set of all outcome which the x omega is less than or equal to x, small x. Now this set is remember that type of particular type of set or interval, that is a Borel set. So we can easily define that q of that. Now the other way, if I know the all value of fx, that means the probability of all that type of interval, then we can construct, or we can get the probability of any Borel set. That is important. So once we can construct that q from f, we just define f from q. So if someone know q, then you can easily find f. But if someone know f, how do you find q? That is important. How do you find q? Because q is defined not only for this type of set. Q is defined on more larger class. Much more set are there. So all Borel sets are there. So can I find all set of probability of any Borel set if I know just the probability of this type of set? The answer is yes. And since it is answer is yes, we should not deals with that q. We always deals with that capital F, the distribution function, rather than the probability distribution over the any set or any Borel set. We just discussed the probability on this special type of set, and from that we can easily find the set of probability of any set, any Borel set actually. So this is the two things. We have to show that we can construct q, we can find q of any Borel set from if we know the capital F. One more thing, and another part is the different properties of that f, the distribution function. So what are the different properties of distribution function? The distribution function, the different properties, number one is this, that is a real valued function. So f is a real valued. Real valued. Is a real valued function defined on real number, defined on set of all real number, and such that number one, it is non-decreasing. So it is increasing, monotonically increasing, non-decreasing function. Sometimes we write f up arrow. This is called non-decreasing or increasing function. Number two, it is right continuous. What is meant by right continuous? Right continuous means that the limit y tends to x plus fx, sorry, fy, is fx. It is called right continuous. This is called right continuous. Number 3, the limit x tends to minus infinity fx. This is 0. And number 4, limit x tends to plus infinity fx is 1. And sometimes we take that as a definition. Sometimes we take that as a definitions, but we can easily prove that the f constructed from that q is actually follows all these properties. Now, some notations are there. Is this is the different notations in this different book is this notation. First of all, this limit x tends to 0, x tends to minus infinity fx is written as f minus infinity. It is not f of minus infinity. It is not that the probability of x less than or equal to minus infinity. It is not that. Remember, it is not that. F of minus infinity is not a number actually. Minus infinity is just a notation. It is not that f of minus infinity is f of x. If a set of all omega belongs to omega such that x omega belongs to x omega less than or equal to minus infinity. That is not. This is actually limit of x tends to infinity fx. The second notation is limit x tends to plus infinity fx is f infinity. So again, f infinity not that f probability of x less than or equal to infinity. Not that. It is a limit x tends to infinity, and the limit y tends to x plus. Sometimes we write this is a x plus. It's x plus. X plus is not a number. It is just notation. So it is right continuous, and the limit we write also like that left hand limit in notation is this limit y tends to x minus that fx fy is fy x minus. So why this is non-decreasing? So first, so one by one, proof one by one. So why this is non-decreasing? Number one. So why it is non-decreasing? This is easy to show. No, it is non-decreasing. What you have to show? It to show that if x1 less than x2, then it should imply f of x1 less than or equal to f of x2, maybe equal. It's not strictly increasing. It is maybe increasing. So it is maybe monotone. How do you show? This is easy actually. What is the f of x1? This is just probability of set of all omega belongs to omega such that x omega less than or equal to x1. And what is f of x2? Probability of set of all omega belongs to omega such that x omega less than or equal to x1, that is x2. Now this set, remember this set is a subset of this is x1 is smaller than x2. So that must be subset, maybe equal subset of this. Any element in left hand side must be element of the right hand side, because if for any omega belongs to left hand side, that x omega is less than or equal to x1, and once x omega less than or equal to x1, x omega less than or equal to x1, that implies x omega less than or equal to x2, because x2 is greater than x1. And therefore the probability of this, we know the subset probability of subset is less than, maybe equal of the probability of the superset. So the proof is complete. And actually by definition this is x fx1, then right hand side is x fx2. So that's why it is a non-decreasing. So in monotonical increasing function. Next, what we have to show? We have to show that this is right continuous. So how do you show this is right continuous? Now right continuous, remember now this to show right continuity, we know that f of x plus, what is actually limit of y tends to x plus fy, that is nothing but limit of some t drops to x ft. What is t drop to x? That means you have to take a sequence such that is a decreasing uh, sequence and decrease to x, and it can be proved in the real analysis. We just omit this part why this is true. So this limit is actually sequential limit, the right hand limit, and this is a, you have a sequence which decrease to x, a sequence decreasing monotonically decreasing sequence. If decrease to x, then the sequential limit is actually equal to the right hand functional limit. We know that if sequential limit, if functional limit exists, and that then the sequential limit is exists and equal, but otherwise may not be true. Otherwise may not be true. If sequential limit exists, then the functional limit may not exist. We know in the real analysis that if the right hand side exists, left hand side may not exist. But since f is monotonically increasing, because since f is monotonically increasing, that is true. For a monotonically increasing function, thus if sequential limit exists, then the functional limit also exists. So that's why these two are equal. Since it is true because of f is monotonically increasing function. And similarly 3 and 4, 3 and 4, that f of plus infinity, that f of plus infinity is actually limit t increase to increasing sequence ft, and just proving, just write some real analysis result, and this is limit t drops to minus infinity, decreasing sequence to ft. Now this is from just real analysis result. This you can find in Apostol books or any other real analysis book. We are not going through this for this proof. We just assume this result, and then we prove it is right continuous. What is right continuous? So it is right continuous because remember that this may not be left continuous, and we have, what is this? This is less than or equal to this, and less than or equal to this, x plus. Why this is true? This is because of the right hand side is just a limit of t tends to x from the right side, but t is decreasing function. So t decrease to x. Since t is a t decrease to x, so x is less than or equal to t. For every t, x is less than or equal to. That's why fx is if you take this thing, then what happens? This actually implies f of x less than or equal to f of t. Now taking limit, therefore you fix your x and you just take the limit of the right side, because it's decreasing limit, and that is nothing but f of x plus by the real result. And we know if some a less than or equal to fx, then limit of fx must be greater than or equal to a. That fx greater than a, then limit of fx greater than or equal to a. Similar for the left hand side, because in the t increase to x. So we have this result. So this is true. Now we have to show that the right hand, that part is equality, that fx equal to fx plus, but that left part may not be equal, that f of x minus may not be equal to fx, that may be strictly less than fx. And if it is strictly less than fx, then the right continuous but right limit exists and left limit both exist, but the limit are not equal. In that case, it's called jump. There is a jump in x, that is called jump discontinuity. if left hand limit, right hand limit is different, then the gap is called the jump of f at x. So if both f x plus and x minus exist and if they are not equal, then it is called jump. So we call x is a jump point of f if and only if fx minus and fx plus both exist, that both the left and right hand limit exist, but not equal. It's not equal to this, and this jump is at x is equal to f of x plus minus f of x minus. Remember that f of x plus is bigger than f of x minus. So jump is always positive here. So x is because f is non-decreasing function. Now we define a new function f star. We define a new function from f star to a real number to 0, 1, such that we define f star as like that for all x belongs to real number. We define f star is just f of x plus, right hand limit at x. Now this x star is also non-decreasing, is monotonically increasing function, and right continuous. And that can be easily proved in using that real analysis thing. You can get the proof is in apostol. We are not going into this. So this is actually this function is right continuous, and it is monotonically increasing function. So why f is right continuous? Because this limit exists, that right hand limit exists and is finite also. Why it is finite? Because f is finite for every t. So the limit is also finite. If it exists, then it must be finite. Now we'll prove it later. Okay, we'll prove it later. Why these two are these are right continuous. This f star is right continuous, but why f is right continuous? We'll prove later. Just before that, we are going to in one more theorem. And the theorem is this: the set of discontinuity point, set of number of discontinuity points of that distribution function f is at most countable. So what do you mean by at most countable? It is either finite or countable. So number of discontinuity point is either finite or countable. So what is the proof of that? The outline of the proof is this. So we take a finite interval of that, and if there are at least n discontinuous point, so let this be if interval with at least n discontinuous point, this continuity point, so we take that interval which has at least n discontinuity point. So that the discontinuity point is x1, x2, xn. These are the point of discontinuity of f between a and b. Then what happens? Then fa, what implies? This implies fa is less than or equal to f x1 minus, and it is strictly less than f x1, because it is the point of discontinuity. Discontinuity cannot be occurring in the right side. It is left discontinuous. It is always right continuous. So it is a left discontinuous. Then again it f2 minus strictly less than f2, and this dot 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 dot, and ultimately it is fn minus in fn strictly less than fn, and which is less than or equal to fn. So these are the jump. There are n jumps, and that take the jumps is pk. Pk is a jump at xk. So pk is a jump at xk. So it is pk is just x f of xk minus f of xk minus for all k equal to 1 up to 2 n. Now what happened? Now these gaps are continuous everywhere other than this point. So this sum over all k equal to 1 to n pk, that is less than or equal to fb minus fa. But remember that fb minus fa is a probability. Is actually probability of x, which is less than or equal to b and strictly greater than a. Now this is a probability, so that must be less than or equal to 1. So how many points? So from that one, what we can get? It follows that the number of points x in that open and semi-open have been closed with the jump px, say, because the jump is number of points, the number of points of x in the what is follows from the number of points x in this jump set is called px greater than epsilon, say, so for some epsilon is at most how many points? At most that fp minus fa by epsilon, that many number, you can have at most. Why? Because you have more than that. If your n is greater than that, and each jump are greater than epsilon, so each jump are greater than epsilon, and if there are, say, this quantity is a 10, this quantity fb minus fa by epsilon is a quality is 10, say it is 10 or 10.5. It can't be more than that jump. It can't be 11 jump, because each jump is greater than epsilon, and if there are 11 jump, then there are 11 into epsilon, and then each jump is this number of jump, this value is 10.5, say, this fb minus fa by epsilon. So that means your fb minus fa is actually 10.5 into epsilon. But if there are 11 jump, that 11 into epsilon is greater than fb minus fa. But we prove that this is less than or equal to fb minus fa. So there are at most this many jump in each AB, and each jump is greater than epsilon. What is the meaning of that? That means for every integer n, the number of discontinuity so the number of discontinuity points with jump, no need of writing that px for that px with jump x, that jump is called px, the jump name as px, no need of that px. The jump is called px. Jump is right, jump is greater than epsilon. Better jump is greater than epsilon. Epsilon positive. Now, the epsilon is positive and that jump is greater than epsilon. So, number of discontinuity point with jump greater than 1 by n. So, how many jump is greater than 1 by n? That cannot be bigger than capital N. Each jump is greater than 1 by n, and if the capital N many jump, the total value is then sum is greater than 1. It can't be true. So it's finite basically. It's finite. Actually, no need of doing this, that fb minus fa by epsilon. We can easily check. We can forget this part also. We can just forget. No need of that two line. Just for every integer, the number of discontinuity point with jump greater than 1 by n is just is actually finite. Is less than or equal to or actually less than, because it is strictly greater than, then it is strictly less than, must be less than n. So there cannot be 10 jumps which each are bigger than 1 by 10. Cannot be. So number of jumps which is greater than n is just finite, which is, so it is finite. That is finite. Finite many jumps. So jump of 1 bigger than 1, it is 0 actually. Jump of bigger than half, it is either 0 or 1. No jump or 1 jump. Jump of 1 by 3 is just 0, 1 or 2. That means how many jumps are there? At most countably many jumps. So that means is the countably many jumps. So therefore there are countably many. So therefore there are countably many jumps. That means number of discontinuities is countable. And this is very important. This result is very important. So what we prove actually, that number of discontinuity point is countable. There cannot be uncountably many number of discontinuity. Now, on this basis of this fact, we actually classify all distribution function. If the distribution function is called continuous, if the function that random variable is continuous, if the distribution function is corresponding distribution function is continuous. If random variable is called finite, discrete finite, if the number of discontinuity is finite. And other than the discontinuous point, the function is constant. And if it is a countable discontinuity and other than the discontinuity is constant, then it is called piecewise continuous constant. Then it is called infinite discrete. And if there are countably or finitely many discontinuity as well as they are not constant in piecewise, then it is called mixed type of random variable. So on this basis of this graph of the function of f, we can say what are the different random variables. So just look on the graph of the f. So what like the graph may be? So the graph may be number 1, that type of thing. One is like that graph may be like that. Say this is always positive. So that may be something like that increasing. So that may be this type of graph. This goes to 0 and this goes to 1. And in this case, this is a continuous. This is the continuous thing. It is continuous. Continuous random variable. Yes. Continuous random variable, the distribution function look like that. If the stepwise is called step function, piecewise constant function, like that, you have maybe this is the left discontinuous, so right continuous. This is the jump, there's a finite jump, and then it is just 1. And it's a 0. Then this is finite discrete. Finite discrete. So x tends to minus infinity 0, x tends to plus infinity already 1. That's because it is already 1 in before going to into the limit. And this is a finitely many jump. And it is a right continuous and left discontinuous some finitely many points. Finite discontinuous, discrete. If it so happens that the graph is like that, let's say your graph is something like that, your right continuous, this, then this is say 1, but it's not reaching the 1, like Poisson distribution. It's going up, then again going up, but don't touch that. Say this up to this, then this up to this, and so on and so forth. And here also not touching, but it may be touched. Here may be touched. And this side is so number of discontinuities are infinite. Number of discontinuities infinite. A number of discontinuity is countable, at most countable. If it is infinite, it must be countable. Then it is called countable infinite discrete. Infinite discrete. And the last one is mixed type of thing. It is not in our syllabus. Last type of function is like that. This may be say this. Then it may be something like say this, or maybe there is a say discontinuity. Then sorry, that must is not that. This is open because you left discontinuous. Then it is this line, this type of thing. Then again jump, again go up, and this maybe this is 1, and then say this is after that this is reach there, say. Or then maybe there constant, and then it is a reach there 1. So this is a mixed thing. This is a mixed type of thing. The mixed, because something a discrete positive probability, and sometimes it is a in continuous version also. So mixed. So if there is jump, then some point has positive probability. If there is no jump, is that as the first case, each point has the 0 probability. In that case, the probability of x equal to x is 0 for all x. But here, what happened? Here, if it is some x1, say it is my x2, it is that point is x3, and this is x4. This has only jump point. That means your that probability of x equal to xi is positive for just I equal to 1, 2, 3, 4, and rest other than that x equal to x, for that is 0 for all x other than not equal to but not belongs to this set, other than this set. X1, x2, x x3, x4. And in the discrete continuous, infinite discrete, if this point is x1, this point is x2, this point is x3, so there is a countable set x1, x2. There is a sequence such that the probability of x equal to xi is positive for all I belongs to the natural number 0, 1, and other than that, probability of x equal to this is 0. Sometimes we call otherwise. We write fx equal to x, probability of x equal to x equal to 0. Probability x equal to x is equal to 0. That is called something called otherwise. Otherwise, what is the meaning of otherwise? Otherwise means x does not belong to that set x1, that x2, and obviously this is called the spec of x. And in the discrete case, the spec of x is this is called the spec of x. It's finite. Here is countable. It can't be uncountable. Now, For the continuous case, the problem is this: that every point this probability is 0. So how do you distinguish the different type of things? So we need a density function there for continuous version, and this is mixed type. Mixed type we are not discussing here. It's out of syllabus. Mixed type. So this is a different type of random distribution function, and different type of random variable. And that what type of random variable is this? We have to find the distribution function, and from distribution function we classify the random variable. So next, what we have to prove? We have to prove that this thing, that what we left, that distribution function is right continuous. So how do you show this? The distribution function is right continuous. So we take a sequence, xn drops to x, that is right hand it is a right hand limit, and that's why this is, since it is drop to x, then x1, then less than x2, less than x3, xn, and everything is greater than x actually, because it is coming from the right side of the x. And this sequence, this xn drops to x. Now f of xn is converts to fx. Why this is true? We have to show this. To show this, we will show that this fn, f of xn converts to, as n tends to infinity, converts to fx. And once we can show this, then it is right continuous. Why? Because by that result in real analysis, that once I just show for once we can show for the sequence, then it is true for functional thing also, using this thing, this result, this first one, that one, this equality. So once a sequence drop to x and that limit exists, then the functional limit exists. And using this real analysis result, we can say that this function is right continuous. But before that, we have to show any sequential limit, that sequence drop to x from the right side, that limit exists, and that limit is equal to fx. So how to show this? To show that, we consider a set AK, set of all omega, such that x omega belongs to that x to xk, that interval. We take this as a AK set. Then AK is an event, because AK is nothing but a inverse image of a Borel set. This is any open semi-closed semi-open interval is a Borel set. So it is just x inverse of that. That's why it's so we can talk about the probability of that. Now xk, what happens? Xk cannot be increased. It's a decreasing. Xk decrease. AK decrease, because it is going smaller and smaller. So here it is x, here it is x1, then it is x2. So as this is coming left, so by that, because this set must be smaller, that is subset, proper subset actually. So this drop to it's a dropping is a decreasing set sequence of set, and so we know, if in the first lecture you see that if the decreasing sequence of set, then in the major theory lecture actually you see, then k limit k tends to infinity, AK is nothing but that limit of this set is just intersection of all such k's, and that is phi. That set is phi. No element in this set, in intersection. No element can be in this this type. So if we take any element, is somewhere it must cross that set element. If we take any element y somewhere, that after some set that some cross that y. So it is a phi set, and since it is a phi set, whatever that limit of this thing, this intersection, that probability of limit of k tends to infinity, AK is 0. But we know this probability is actually limit of probability. That is in measure theory, we prove it for any general measure also. So it is done. So we prove it. So that is a fxk. This is the fxk. No, this is not the fxk. This is what? Oh, this is actually this. What is the probability of ak? This is actually f of xk minus f of x, right? Because it's from here to here, from here to here, this part. So this is this part minus this part, this probability of this. So done. This goes to 0 as k tends to infinity. So fxk goes to fx. So it is right continuous. And similarly, we can prove it is that f of infinity is 1 and f of minus infinity is 0. That is easily you can do this because we consider the sequence of set like this, and that sequence is decreased to say minus infinity, and this is a decreasing sequence, and this is a subset, a super. Then the next one is a subset, and like that. And since a decreasing sequence and decrease to 5, and this decrease to 5, this set decrease to 5, because as xn tends to infinity minus infinity, this decrease to 5. And again by the similar thing that limit interchange limit and probability, you can change the limit and probability interchange. The probability of limit is the limit of the probability. So this is 0 again. And for the plus infinity, what you have to show, how do you prove it is plus infinity? It is similar. You have to take a increasing sequence. You have to take increasing sequence, increase to infinity, and similarly there is an increase, then it will be increasing sequence. That set, then next one is superset of that, and is increased to r. Actually, this set is increased to r, and as x tends to infinity, this set actually increased to whole real number set, and we know the probability of this whole real number is 1. That's why it's 1. So we complete the proof here, and this is for this lecture. And next we discuss different type of random variable, and then their expectation variance and any other thing also.